Hi everyone, we are Group 5 and today we will present on our project which is First Ordinary Differential Equation ODE based problem on the linear ODE which is non-HOMO. There are 4 members in our group which is CHANG, metric number 224580, KHOO Yishan, metric number 225397, Liu Ge, metric number 218466, and there's me, Chu Mei Wing 224324.
And before we go into details, I'm going to first introduce the general project description. And it is a relation project towards ECH 3123 material balance and ECH 3124 energy balance. And it aims to produce 70% weight over weight total weak nitric acid with feedstock of 1 million ton per annum, and the method that we use is dual pressure to produce the weak nitric acid. And the technology that we use is the Baymax technology. And the units chosen for our math project to calculate is reactor 1 and condenser 2. And there are two methods that we chose to solve the ODE. And the first one is integrating factor, which is the IF method. And the second one is variation parameter method, which is the VP method.
The first unit, which is reactor 1, was selected in our application of ordinary differential equation. This reactor is built out for ammonia synthesis at specified temperature and pressure, which is 500 degrees Celsius and 270 to 350 atmospheric pressure respectively, by passing hydrogen and nitrogen mixture in a 1:3 volume ratio. So, this is the block flow diagram which shows that 100 mole of basis consists of equal amount of nitrogen and hydrogen gas enter the reactor 1 and come out with 40 mole nitrogen, 20 mole of hydrogen, and lastly 20 mole of ammonia gas. The feedstock per annum in this project is 1 time 10 power of 6 ton of gas mixture. To aid for the further calculation, we will convert the unit in tons to kilogram. So the answer obtained will be 114,150 kilogram per hour. In order to obtain the volume of gas mixture, we use the ideal gas equations and substitute the given value, and we would get 2,445.39 liter. To prepare the first order of ordinary differential equation, we apply the concept of balance law. In this case, dy dt is equal to nitrogen inflow rate minus nitrogen outflow rate. Dy dt represents the rate of change of amount of ammonia accumulated in the reactor, while y bracket t is the amount of nitrogen accumulated in the reactor. So based on the material balance, the equation that we use is input minus output plus the generation minus the consumption equal to 0. So in this context, we know that accumulation rate is equal to inflow rate minus outflow rate. There are two assumptions have been made, which are 15 mole of nitrogen is initially accumulated in the reactor, and the nitrogen outflow rate is 350 liters per hour. This is the calculation of nitrogen inflow rate. Based on our question, there is 50 mole of nitrogen in the gas mixture. To obtain the volumetric flow rate of the gas mixture in the inlet stream, we use the equation of volume equal to mass per unit density. The density of this gas mixture is 0.505 kg/cm3. By substituting the value, we will get the final answer as 226.039 liter per hour as the volumetric flow rate. In this case, there is 50 mole of nitrogen contained in a 2445.39 liter of gas mixture. So, 50 mole of nitrogen will be divided by 2445.39 liter and times with the 226.039 liter per hour, and we will get 4.622 mole per hour at the inlet stream. calculate the nitrogen outflow rate, there is same concept being used. In this case, the volumetric flow rate at the outlet stream is 350 liters per hour. In this case, the accumulated nitrogen in the outlet stream of the reactor is remain unknown. Hence, we derive 0.143 Y bracket T. Applying the balance law, we know that dy/dt equal to nitrogen inflow rate minus the nitrogen outflow rate. Using the previous answer, which is 4.622 molar flow rate at the inlet stream, we would derive the equation as dy/dt equal to 4.622 minus 0.143 Y bracket T. Converting this equation into standard form, we would get dy/dt plus 0.143 Y bracket T equal to 4.622. Now, I'm going to use the method of integrating factor to obtain the general solution. Firstly, we have derived ODE, which is written as dy/dt plus 0.143 Y bracket T equal to 4.622. In this case, P bracket T is 0.143, while the integrating factor that represented by V bracket T is exponential 0.143 T. As such, by substituting those values, we would obtain the general solution with the constant C, which will be written as y equal to 32.32 plus the C exponential 0.143 T. The assumptions have been made previously, which is T equal to 0 and the Y bracket T is 15 mole nitrogen that is accumulated in the reactor initially. Using those values, finally we would get the particular solution that is written in Y equal to 32.32 minus 17.32 exponential negative 0.143 T.
And the second method that we're going to try to solve our ODE is called the variation parameter method. And in this case, the ODE equation that we already derived is dy over dt plus 0.143y is equals to 4.622. And the first step that we want to use while using the variation parameter method is to change the ODE equation into homogeneous ODE and let Rx equals to 0. And in our case, the equation will be dy over dt plus 0.143y is equals to 0. And step 2 is to organize the ODE equation in step 1 and then integrating by both sides. And we'll eventually come up with the answer that YH is equal to exponential negative 0.143t. And the third step is to construct general solutions for the inhomogeneous ODE by using variation parameter Vx. And as you can see, y is equals to YH plus VT. And V stands for the variation parameter. And the fourth step is to get dy over dt. And how do we get the dy over dt? Well, the main solution for that is to substitute the YH values from step 2 into the equation in step 3, and then we take the derivative of that. Using the multiplication rule, we can come up with the equation in step 4. And step 5 that we're going to take while using the variation parameter method is to substitute the values of dy over dt and YH into the ODE and obtain the first order separable ODE. And after we substitute the values in, the equation will become a equation related to V. So we can get that dV over dt is equals to 4.622 exponential 0.143 dt. And after we organize it, we can integrate on both sides and eventually get Vt is equals to 32.3147 exponential 0.143 t plus c. And the sixth step that we're going to take is to substitute the Vt values in the variation parameter equation and get the y. And we got the equation. After we substituted, we can get that y is equals to 32.3147 plus c multiplied to exponential negative 0.143t. And the final step is to calculate values of c. We are going to assume that t equals to 0 and yt equals to 15 moles of nitrogen accumulated in the reactor. And after we substituting the numbers in, we can calculate that c is equal to negative 17.32 and eventually come up with our final equation, which is y equals to 32.3147 minus 17.32 exponential negative 0.143t. And the application of our ODE that we derived is to calculate the time needed to accumulate certain moles of nitrogen in our reactor. And here's this hypothetical question that we set up. Calculate the time when the number of moles of nitrogen accumulated is 10 moles in the reactor by using the particular solution. And how do we solve using our ODE? We substitute the numbers that 10 moles into our yt, and now we have an equation. 10 equals to 32.32 minus 17.32 exponential negative 0.143t. And now we have our equation. We just solve it, and we'll eventually come up with a solution that t is equals to 1.78 hours. So the time needed to accumulate 10 moles of nitrogen in the reactor will be 1.78 hours. So that is how we apply our ODE and our particular solution.
The second unit that we have chosen for our project is the second condenser. It functions as a cooler to lower the temperature of the product stream of the ammonia combustion. The temperature in this condenser is set at below 50 degrees of Celsius to change the phase of the water vapor from gas to liquid state. So as you can see here, this is our block flow diagram for condenser 2. All of the molar flow rates are stated one by one all over here. And the initial temperature before entering the condenser 2 is 748.89 degrees of Celsius. And the final temperature leaving the condenser 2 will be 45 Celsius.
Moreover, in order to create a first-order ODE, we will apply Newton's law of cooling in this case. For information, Newton's law of cooling states that the rate of loss of heat from a body is directly proportional to the difference in the temperature of the body and its surroundings. As shown in this equation, d capital T over d small t equals to negative k multiplied with T minus T naught, where d capital T over d small t as the rate of change of temperature in condenser 2, k as the coefficient of Newton's law of cooling, capital T as the temperature in condenser 2 in T degrees Celsius, and T naught as the initial temperature in condenser 2 in T degrees Celsius. First of all, as you can see, the first order ODE is in separable form, so we can integrate both sides of the equation. The left-hand side is integrated with respect to capital T, whereas the right-hand side is integrated with respect to small t. After integrating both sides of the equation, we obtain an equation which is ln capital T minus capital T naught equals to negative k small t plus c, where c is the constant of integration. Next, we exponent both sides of the equation to find equation capital T. So e power capital T minus capital T naught equals to e power negative k small t plus c. Then e power capital T minus capital T naught will be equals to capital T minus capital T naught only, whereas the other side equals to e power negative k small t multiplied with e power c.
In this step, we are letting A equals to e power c to make it look more neat. After rearranging and rewrite the equation, we will obtain a first order ODE which is capital T equals to capital T naught plus A multiplied with e power negative k small t, where A is a constant determined by the initial condition. Given that the initial temperature entering condenser 2, which is capital T naught equals to 748.89 degrees Celsius, we can substitute the value into the equation that we just obtained. In order to find the value of K in the said equation, there are two assumptions must be made, which are temperature is changed from 748.89 degrees Celsius to 350 degrees Celsius in 5 hours, and temperature is changed from 748.89 degrees Celsius to 45 degrees Celsius in 10 hours. After that, the two assumptions are substituted into the equation. From assumption 1, we obtain an equation 1 which is A multiplied with e power negative 5k equals to negative 398.89. On the other hand, from assumption 2, we obtain an equation 2 which is A multiplied with e power negative 10k equals to negative 703.89. Now we can get the value of k by solving simultaneous equation by using the said equations. As a result, we know that k equals to negative 0.113, and now let us substitute value k and value capital T naught back to our ODE. So d capital T over d small t equals to 0.113 capital T minus 84.62. Lastly, for getting the first order ODE, we rearrange the equation and it becomes d capital T over d small t minus 0.113 capital T equals to negative 84.62. That's the final answer for this part. Furthermore, there are two methods to solve the first order ODE, which are integrating factor method and variation parameter method. In this section, I am using integrating factor method to solve the problem. First of all, as you can see, this is our general form of linear first order ODE, which is d capital T over d small t plus function f in terms of small t multiplied with capital T equals to function r in terms of small t. And the ODE that we just obtained from previous part, which is d capital T over d small t minus 0.113 capital T equals to negative 84.62. We compare the ODE with the standard equation to get the value of f equals to negative 0.113 and r equals to negative 84.62. Then, to get the integrating factor, which is also known as IF, we use the equation IF equals to e power integrate f with subject to small t. And we will obtain the value of integrating factor equals to e power negative 0.113 multiplied with small t. Next, now we substitute the IF into the equation, which is capital T multiplied with IF equals to integrate R multiplied with IF with respect to small t plus C. After calculating and rearranging the equation, we will get capital T equals to 748.85 plus C over e power negative 0.113 multiplied with small t as our general equation. Subsequently, to get the particular equation, assumption 2 small t equals to 10 hours and capital T equals to 45 degrees Celsius are substituted into the general equation. As a result, the value of C is determined as negative 227.37. At last, we substitute the C value into the general equation Thus, the particular equation of condenser 2 is capital T equals to 748.85 plus bracket negative 227.37 over e power negative 0.113 multiplied with small t, where capital T is temperature in degrees Celsius and small t is time in hours.
So now we'll be moving on to the second method of solving ODE, which is variation parameter, VP. Alright, let's begin. So by using variation parameter, the general form of linear dE will be dt over dt plus ft t equals to RT. So from the ODE from above that we already obtained just now, it will be dt over dt minus 0.113t equals to negative 84.62. So as you can see here, the RT, which is negative 84.62, doesn't equal to 0, which means it is inhomogeneous. So therefore, we must change it to homogeneous ODE first, which is 0 for the RT value. So this will be our homogeneous ODE, which is dt over dt minus 0.113t equals to 0. So after equating RT to 0, we solve the corresponding homogeneous ODE. dt over dt equals to 0.113t, and then we will integrate both sides. We will get ln t equals to 0.113t, and we'll add the exponential here, and the final t will get t equals to exponential 0.113t. So after getting the final t, we shall introduce the variation parameter equation, which we will multiply the t equation with vt, which is the variation parameter equation. And now we should find the dt over dt by applying product rule, which is u and v, and then we have to differentiate the u and v, and we'll substitute the value into our dt over dt by applying the product rule. So the value we get will be exponential 0.113t multiplied with v differentiated v plus 0.113 exponential 0.113t multiplied with a regular v. So now we will substitute the t equals to exponential 0.113t multiplied with vt from above, and the dt over dt just now into our ODE to get the vt. So this will be our ODE, and let's see what's the next step. So for this step, we will substitute the dt over dt and also the t equation that we obtained just now into our ODE, which then we will simplify it, and this is the equation that we get, which is exponential 0.113t multiplied with a differentiated v equals to negative 84.62. And then we will replace the differentiated v with dv over dt because both of them means the same thing. So we'll get dv over dt exponential 0.113t equals to negative 84.62. And then we will move the exponential to the right hand side, which then we can integrate both sides in order for us to get the v. And the final v, we will get v equals to 748.85 exponential negative 0.113t plus c. Okay, so after we already get the vt from the steps before, we shall substitute it into our variation parameter equation and get the t. So the t that we get will be the general solution, which is 748.85 plus c exponential 0.113t. You can also rewrite this equation as 748.85 plus c over exponential negative 0.113 t. Both of them means the same thing, so you can choose either one. To obtain the particular equation, assumption 2 is used. So for assumption 2, which is t equals to 10 hours and the capital T equals to 45 degrees of Celsius, we substitute both of these value into our t equation, which then we will obtain the c value, which is negative 227.37, and then we can get our particular solution, which is t equals to 748.85 minus 227.37 exponential 0.113 t. So after developing a mathematical model for our condenser 2, which is the particular solution just now, t equals to 748.85 minus 227.37 exponential 0.113 t, we shall use this equation in our application problem. So let's take a look at the problem. A condenser is used to lower the temperature of the product stream of the ammonia combustion. The final temperature of the air stream leaving the condenser is 98 degrees Celsius. How long will it take for the condenser to cool down the air stream to that temperature, which is 98 degrees Celsius? Now we should replace the 98 degrees Celsius into our capital T. And then after solving the mathematic problem here, we will get the small letter t equals to 9.31 hours, which is roughly 9 hours. And we can conclude that the condenser takes about 9 hours to cool down the airstream to 98 degrees Celsius.
And at the end of our video presentation is discussion and conclusion for our project. Two mathematical models are developed in this project. The first one is y equals to 32.32 minus 17.32 exponential negative 0.143 t, which is used to calculate the amount of nitrogen accumulated in the reactor over time. And the second one is t equals to 748.85 minus 227.37 exponential 0.113 t to forecast the temperature for the outlet stream from the condenser over time. Both equations generated by using the integrating factor and variation of parameter method, and provided values tools for optimizing the nitric acid production process by enabling better control for reaction conditions and enhancing the overall efficiency and safety for our operation. And that will be the end of our video presentation, and thank you very much for listening.
And that's all from us. Thanks for watching.